Hi everyone, welcome to part 1 of a lecture where I'll be covering strengthening methods in metals. In this lecture, I will cover the 5 main techniques for strengthening a metal, as defined by an increase in the yield strength. The very first thing that needs to be appreciated when applying any technique to strengthening a metal with a given composition is that whenever the yield stress is increased, this will be accompanied by a decrease in ductility. The modulus for all the techniques described does not change significantly. What I mean by this is that it doesn't change by any more than a few percent for all methods described. What does change is the yield strength, the point where dislocations start to move and interact. Therefore, anything that is done to offset this point will further inhibit dislocations from moving throughout plastic deformation. When I say for a given metal, or when comparing one being stronger than another, I mean that with a fixed composition and state. Let's get on to our first method. The first method is strain hardening. In an early lecture, I described a uniaxial tensile test whereby multiple loadings were applied. I showed 3 different loadings of the same specimen, whereby the subsequent point where it yielded was the stress level which was last attained in the loading prior. This is a clear example of strain hardening, whereby it is more resistant to deformation based on prior plastic loading. You can see that the yield stress attained in the final loading event exceeds the first by a fair margin. This is observed in practice to varying degrees. It is important to highlight that this must be done at ambient temperatures. At higher temperatures, this is not effective, which will be covered in subsequent lectures. In order to appreciate why strain hardening is an effective strategy, we will need to examine why. I have already described an edge dislocation and the method by which it moves. Due to the extra plane of atoms, there is a local compressive strain field on the side of the dislocation which contains the extra half plane of atoms. A balancing tensile strain field occurs immediately below this. It is compressive at the top as the mean distance of atoms here are marginally closer than at the bottom, where they are further apart. These fields clearly move with the dislocation, and they can interact with fields associated with other dislocations. Let's see how. If I were to place 2 edge dislocations beside each other as depicted, there will be a repulsion between them as the respective strain fields would repel against each other. Attempting to move one to the influence of the other and vice versa will require a significant amount of additional shear stress. If instead I were to invert one of the edge dislocations with respect to one another to create a so-called negative dislocation, as defined by Berger's vector following the same convention for each, then there will be an attraction between the compressive strain field versus the tensile strain field. Indeed, there would be a situation where the dislocations would coalesce and cancel. The positive-positive type of interaction is far more common than the positive-negative type of interaction during deformation. Driving a pair of positive dislocations towards each other requires significantly more shear stress than driving an isolated positive edge dislocation through an otherwise defect-free lattice. Dislocations would move until they encounter each other and then start to pile up on top of each other. Conversely, driving a positive and negative dislocation toward each other is far easier, and the half plane associated with each edge dislocation results in the formation of a full plane, thereby annihilating both dislocations. This results in a perfect crystal, at least locally. This type of event will detract from the overall dislocation density. However, as we've seen previously, the net dislocation density increases as deformation proceeds. The net contribution of this event is therefore minimal under ambient conditions, but it does become important at elevated temperatures. So where does all the extra dislocation density come from? The answer is dislocation sources, one of which is the Frank-Reed source. We've already described dislocations as line defects. A length of dislocation can be pinned by the same incorporations in the lattice that are responsible for their creation. vacancies, inclusions, etc. These terminate a line length of dislocation and prevent the ends from moving as shown in frame 1. Once this line encounters a shear stress, it will move away from the pins and start to bow. This will continue as shown in frame 3, whereby the dislocation line will loop back on itself. We've already discussed how dislocations can bow and change direction when we covered mixed dislocations. At a critical point, the dislocation will join on itself, creating a loop around the initiating pinned length, and the originating line will return. This repeats over and over again as shown on the top left of a wafer of silicon. This is one of the principal ways that dislocation density can dramatically increase with deformation. We can relate the dislocation density directly to the rate at which the yield stress incrementally changes. This can be related to the shear stress that is required to move a dislocation as a function of dislocation density. Some constant value of shear plus some constant times the root of the dislocation density is a valid expression for single crystal systems. The constant K has a few more physical dependencies and is actually a function of crystal type, the shear modulus, and the Berger's vector magnitude. But this form of the expression clearly demonstrates that as the dislocation density increases by sources, it becomes increasingly harder to move them around. This expression is actually what was used to calculate dislocation density from macroscopic observations of plastic deformation in single crystals. For polycrystalline systems, things get more complicated, but there is a way of empirically capturing the degree of strain hardening. This can be accomplished by capturing a measure of cold work. One common way of doing so is to tabulate the change in cross-sectional area or some other critical dimension of a component as it's being deformed. For example, in a uniaxial tensile coupon, one could use the change in cross-sectional area as a measure of cold work, expressed as a percentage. Plotting the relationship between cold work and the yield stress, it can be seen there are very different responses depending on material to cold work. The shapes of these curves of yield stress versus percent cold work are quite similar to the plastic portion of the true stress-strain curve. They clearly demonstrate that the yield stress increases with increasing amount of prior deformation. If we were to extract all of the stress-strain curves that went to decide the yield stress versus percent cold work for low-carbon steel, for example, we would end up with the arrangement on the right. This clearly depicts how ductility is exhausted as cold work is imposed. Also note that the ultimate tensile strength is also increasing with cold work, as is the shape of the initial region of yielding. This is because there are other strengthening mechanisms at work beyond purely strain hardening for steels, something we'll discuss in coming lectures. In this part of the lecture, we've reviewed only one type of strengthening mechanism. There are a further 4 remaining ones to discuss. However, the role of dislocations and how they interact during plastic deformation is crucial to understanding the subsequent methods. However, for all strengthening methods, there is a trade-off between increasing strength and decreasing ductility, with very few exceptions. While at the granular level, the phenomena of increasing dislocation density has been employed to describe this behavior. From a more empirical standpoint, this phenomenon can be captured with some measure of prior deformation, such as the percent cold work. Until next time.